Okay, maybe we can start now. It's a good time. So we're happy to have Yi-Zhuang tell us about symmetric mass generation. And so please.
Yeah. Okay. Yeah. Thanks. Thanks, the organizers, for inviting me here and to this fantastic workshop. And I have been enjoying the talks and conversations. So today I'm going to share with you the topic of symmetric mass generation, which is basically a new mechanism to give fermion a mass without breaking any symmetry, without generating any fermion bilinear condensation. So Juven and I wrote a review paper on this topic and just published recently. And this is you are welcome to read this. It's an open access journal. You are not recommended to read our archive version, however, because there's still some mistake there. We haven't updated, but it's this public version is the correct version. We will update the archive soon, maybe. So okay, so we'll be talking about mechanisms to give fermion a mass. Then let me first review what is our conventional understanding of fermion mass. So maybe the simplest model or most familiar model that we know about fermion mass is fermion bilinear mass. So this fermion bilinear mass basically appears in a very simple model like this, which describes relativistic fermions, which denoted by this fermion field psi in d-dimensional space-time, which has a Dirac action. And here I will be a little bit sloppy that this phi can either be a Dirac fermion if it's complex or Majorana fermions if it's in the real representation. I won't distinguish them very seriously, but in any cases, you would have a fermion bilinear term, and this mass term is kind of the only parameter you can tune in this theory, which gives rise to a fermion bilinear mass. So if you add this term, if you turn on this M, and it has several consequences. First of all, it creates an energy gap in the fermion excitation spectrum. You can see that pretty easily from this action. If you take the saddle point, derive the saddle point equation of this action, this gives you the equation of motion for this fermion field. And if you solve this equation of motion, you find the unshared condition that indicates that all the fermion excitations in this system, they are quasi-particles, and they form two bands. And then the excited band and the occupied band, there is a gap between them. And the gap is of the size that is proportional to the parameter m that you inserted in your theory. And it has another consequence that if you try to calculate the fermion two-point correlation function in this theory, and you will find that it's short-ranged, meaning that the correlation function will decay exponentially with the separation of the two fermion operators. And the decay length or the correlation length is finite in this case, and this correlation length will be inversely proportional to the mass parameter of the fermion. So that's basically two consequences that you add a bilinear mass to a relativistic fermion in any d dimension. However, that is basically a free fermion understanding, right? So the question is, how do we define fermion mass more generally if there is interaction? Well, if there is interaction, you can't easily solve the equation of motion because it will be nonlinear. And more seriously, the notion of quasi-particle may not even be well defined under interaction. So it doesn't really make sense. What does it mean by a dispersion relation? So in that case, you can't simply say that, oh, mass is just a term that appears in like a p squared plus m squared, take a square root, that m is mass.
But
it's not like...
Sorry, usually
yeah.
we have to reach a ground state and excited.
Yeah. You still have a ground state and excited states. So the proposal is that you can use this excitation gap to maybe define the fermion mass. So a formal statement is like you can still define two-point function of a fermion field given any action can be interacting, and then the fermion mass, you can think of it as the inverse correlation length, meaning that if this correlation function follows a power law behavior, then we say the system is massless, and if it has an exponential decay behavior, then you can define the mass as the 1 over correlation length. If if you assume relativity and Lorentz symmetry, then it's basically the same as saying that its mass is the excitation gap of fermions in the many-body spectrum.
So this will include cases where mass is spontaneously generated.
Yes, 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 yes. Okay, so given this understanding, basically now I can explain what does it mean by fermion mass generation, right? We want to create a mass, which means the problem of fermion mass generation is try to find a mechanism starting from gapless fermion, which doesn't have a mass, and try to create an excitation gap in these systems for the gapless fermions, or try to make the correlation length of a fermion system of this fermion two-point function short to make them finite, basically. So that's basically the question. And then the way to do this, the standard way, or maybe we are all very familiar, that is the Higgs mechanism, which basically you can condense a fermion bilinear mass. Even if you start from a theory which doesn't add this mass term explicitly, it can be generated dynamically due to fermion interaction, maybe. But this mechanism necessarily involves spontaneous symmetry breaking or gauge Higgsing. If some of the symmetry group is gauged, then basically creating this mass term may Higgs the gauge field. So examples appears, for example, in condensed matter, we talk about BCS superconductor, which basically breaks the U1 charge conservation symmetry to Z2, and then it creates a gap at the Fermi surface. So that is a fermion mass generation under the Higgs mechanism. In high energy physics, we also have electroweak Higgs, which breaks the SU2 weak cross U1 hypercharge to U1 EM. So this is our standard understanding, but this may not be the full story of fermion mass generation. So the topic I want to discuss today is basically, can fermion acquire a mass or gap without spontaneous symmetry breaking? So basically, in the following talk, I will try to ungauge all the fermions such that I will only talk about fermions that is charged under global symmetry. And then I will treat all the gauge group that couples to the gauge field that couple to the fermion as background gauge field. But in order to answer this question, there is some intuition or experience from condensed matter. We do have examples in condensed matter physics which kind of create a gap for a fermion system without generating any symmetry breaking. So there are examples like Mott insulators that you can open a gap just by charge repulsive interaction, and there are Kondo insulators which has gap opening by Kondo spin interactions. So the idea is that you can use interaction to open a gap in a fermion system, and basically we will wonder whether this kind of mechanism will also have anything to say to relativistic fermions.
And you need these interactions to be strong in general?
Yes, okay. Yes. Because basically, I think in three-dimension or higher, right? Four fermion interaction is irrelevant, perturbatively irrelevant at the free fermion fixed point. So generally, if you just add a little bit interaction, it doesn't really do anything to the system. So you need a rather strong interaction. So this is intrinsically non-perturbative, this effect of strong interactions. So that's why it's not easy to analyze in general. Okay, so this diagram, I try to summarize the current knowledge about fermion mass generation, all the different mechanisms that we know about how to give mass to a fermion. So it requires you to know the symmetry groups. You need to specify the space-time internal symmetry of your system. And then the system is fermionic, meaning that at least you have some fermion fields which transform under the symmetry under certain representation. This R psi G. It means that the representation of the field under the symmetry group G. So basically, all different mechanisms can be nicely classified using these symmetry principles by answering three questions. So the first question is whether there exists a symmetric bilinear mass term. So you are given the fermion representation and you're given the symmetry, right? Then you can determine whether I can write down any term like psi bar psi, which doesn't break any symmetry. So if that exists, if the answer is yes, then basically symmetry doesn't forbidden you to add this term to your Lagrangian, then you just add it. Then add it explicitly, it will create a fermion bilinear mass. So that is the trivial way to give fermion a mass. However, in many cases, the answer is no. There does not exist such a symmetric bilinear mass. Then you have to answer the second question, whether or not you wish to preserve the symmetry G. So if the answer is no, you don't care the symmetry, then even if you can't add this bilinear term explicitly, you can still add it dynamically by spontaneous symmetry breaking. You can spontaneously break the symmetry, maybe fully break or partially break, and then you can add this bilinear term still. You can generate it, meaning that this bilinear expectation value will not be 0 in your ground state, although your action is still symmetric under the symmetry, but your ground state may not be symmetric under the symmetry, such that in your ground state, you have this bilinear mass, and fermion spectrum will also be gapped. So like Anderson-Higgs mechanism, spontaneous symmetry breaking, chiral symmetry breaking, they all belong to this category.
Sorry, I don't understand why you're putting Anderson-Higgs with spontaneous symmetry breaking.
Okay.
That's not the same. One has an order parameter and the other one doesn't.
Yeah. But if you treat all the gauge field as ungauged, then that's...
That's true, but I mean, if you treat them as dynamical...
Yeah, then that's not...
Then they do provide a mechanism of symmetric gap generation.
That's true. So secretly speaking, there is actually no true difference between symmetric mass generation and the conventional Anderson-Higgs mechanism. That's true. So as you will see, that theories that describe symmetric mass generation actually uses Anderson-Higgs mechanism. But let's say if so you can cross this out. So let's say if we only consider the fermion only charge under global symmetry, then there is still a distinction. Yeah.
So can I ask you a basic question? For the Mott insulator example you mentioned, where is that in this tree?
It's not very obvious, but because it's not relativistic fermion, it's Fermi surface.
Yeah.
So currently it's outside the tree.
It's outside. Okay.
What
Yeah.
about
But,
on honeycomb lattice?
but-
Can make one relativistic.
Yeah. But in that case, then you need to specify the symmetry. It's a bit subtle, and in that case, there's a Lieb-Schur-Matisse anomaly. And then, in order to saturate the anomaly and open a gap, sometimes you end up with a spin liquid phase when you go to the Mott insulator, and then that leads to this topological mass generation. If you need to use topological order to saturate anomaly.
Say you're at the commensurate filling when you're allowed to.
Yeah. Then you can create symmetric mass generation.
Okay.
Yeah, in that case.
Oh, but it's still a complicated thing. It's not a simple part of the tree.
I should say, in general, Mott insulator, it's not a single class.
Okay.
It may split into different parts in the tree, because sometimes you can crank up interaction, create a Mott insulator, but they're also spontaneous, break symmetry, and develop antiferromagnetic order. So it's not a single thing. Yeah.
Thank you.
But however, if the answer to the second question is yes, that means you want to preserve the symmetry. That is the non-trivial thing. Then you have to think about it, how to do it. That basically fall into this category called symmetry extension, where you try to extend the symmetry instead of restrict it, instead of breaking it, in order to avoid the obstruction of mass generation. And then these category further split into two different classes, depending on whether the symmetry G is anomaly free. So if it's anomaly free, then it's symmetric mass generation. You can open a gap trivially, meaning that it doesn't have any consequence after you open the gap. Everything looks like perfectly like a product state, basically. And then in the other case, when the anomaly is not free, then you have to saturate the anomaly by some topological quantum field theory. Okay, so that's basically the general idea. Then today's topic is focusing on this part, this corner, symmetric mass generation. So it basically is a mechanism where the system has some symmetry, and the symmetry is anomaly free, so there's no obstruction towards gapping. However, the symmetry itself is still very restrictive, that the symmetry doesn't allow any fermion bilinear mass, so you can't just add this explicitly to your action. But you know you can do something because anomaly is free, you can gap it. So that's why you need to use interaction to do that. So that's the idea. Okay, so now let me go through some examples, and at this point, any questions? Okay, so let me introduce some examples. So the first example I want to talk about is Fidelkowski-Taif model, which is a symmetric mass generation in 0 plus 1D. It's just a quantum mechanical system. And it is, maybe you can say it's the first and simplest example of symmetric mass generation. And this is discovered by Fidelkowski and Taif in 2009, which is more than 10 years ago. It basically describes a collection of Majorana fermions in 0 plus 1D. Just you think in a site, basically, in a single site. So these Majorana fermions are described by the Majorana fermion operator chi subscript A. And then these operators, they satisfy the Clifford algebra. That's the definition for these operators. And they are Hermitian operators. They are on-Hermitian conjugates. They can be viewed as the real and imaginary parts of the fermion creation annihilation operator, in the sense that you can combine a pair of Majorana operators and then create the complex fermion creation annihilation operator out of that. And based on that, you can also even define the fermion number operator, C1 dagger C1, where you can show that this number operator only has two eigenvalues, 0 and 1, which correspond to whether the fermion occupies, I think 0 is not occupied, 1 is occupying this particular complex fermion mode. So that's what we know. And then we just want to consider a system made of these Majorana operators, and then the system also subject to some symmetries. So the two very important symmetries that we want to impose to this system is, the first one is a time reversal symmetry. Don't worry about this name of time reversal. Condensed matter just call any anti-unitary symmetry as time reversal. So basically, it's an anti-unitary symmetry that does nothing to your fermion operator and that changes the sign of imaginary unit I. Basically, complex conjugate any complex number you encounter in your Hamiltonian. And then another symmetry is the fermion parity symmetry, which flips the sign of this Majorana operator. And then the question is, what will be the Hamiltonian operator that describes this quantum system made of Majorana fermions while preserving this so-called time reversal and fermion parity symmetries? Well, if you look at the fermion parity symmetry, it gives a minus sign to every Majorana operator, right? So in order to preserve this symmetry, your Hamiltonian must contain even number of Majorana operator in order to cancel this minus sign. So the Hamiltonian must take a form like you have bilinear term, you have 4 fermion term and 6 fermion term and so on. And then there will be coefficient, of course, in general, in front of every terms. And this coefficient, this u, is real. Especially if you look at this here, that means I times u, the overall coefficient in front of the bilinear term, is purely imaginary. And this is basically required by the hermiticity of the Hamiltonian. And then you want to also ask the Hamiltonian to respect the time reversal symmetry. But the time reversal symmetry does nothing to this fermion operator. It just takes I to minus I. So basically, every term that comes with imaginary coefficient will be ruled out by the time reversal symmetry. For example, the bilinear term. So if you want to consider a fermion system of such without any interaction, then you also don't have these 4 fermion and higher fermion terms. Then the Hamiltonian is very simple, actually. Hamiltonian is just 0. You can't write down anything meaningful that protects, that respects both of the symmetries. So in this case, what do I mean? What's the consequence if there's a quantum many-body system, Hamiltonian is 0? The meaning basically is all the states in this many-body Hilbert space are degenerate. That means there is no fermion, all the fermion excitations are gapless in this sense, because there's no energy separation between the odd and even fermion parity states. So how many states are there in this degenerate space? Well, you can simply count that by counting how many Majorana 0 modes you have in the system. So every pair of Majorana modes, you can create a complex fermion mode out of that. And the complex fermion mode, for example, Chi1, Chi2, you can create a complex mode. And then that mode can be occupied or empty, so that leads to twofold degeneracy. But if you have 2 n Majorana modes, then you have 2 to the power n dimensional Hilbert space. So that's basically the number of degeneracies you have in the system. So when the Hamiltonian is 0, and in this Hilbert space, basically half of the state is even fermion parity, half of them is odd fermion parity. So, but there's no gap between them. So any fermion excitation, basically, that's an excitation that takes you from the even parity state to the odd parity state, but there's no gap. So basically, all the fermion excitations are gapless in this sense. So without interaction, the conclusion is that in this system, without interaction, if you want to preserve the time reversal and fermion parity symmetry, then the degeneracy cannot be lifted, no matter how many Majorana zero modes you added to the system. So this kind of a very robust degeneracy looks like a Z-classified anomaly because you can't lift it, no matter how many Majorana modes you put into the system. So you can create an index which simply counts the number of Majorana modes in the system, and it's never trivial. It seems like that, but it's not true, because we have only considered at fermion bilinear level that is the case. And with interaction, that is not the case. So what can we do with fermion interaction? Well, that is the proposal of Fedorkovsky and Kitaev. They say you can consider 8 Majorana modes. So let's consider that the system has 8 Majorana modes, so 8 these kind of operators. They can be grouped into 4 complex fermion modes because every pair forms a complex fermion. So I will denote these complex fermion operator as CA equals 1, 2, 3, 4. Then it is possible to turn on an interaction, and the Hamiltonian reads like this. It's like a C1, C2, C3, C4 annihilation operators plus Hermitian conjugate plus the creation operators. So you can see that this Hamiltonian simply basically simultaneously creates 4 fermions. And actually the system only has 4 complex fermion modes. It basically simultaneously creates them or annihilates them. So the Hamiltonian, the only effect of the Hamiltonian is to hybridize the fully empty state and with the fully filled state. And all the other states in the Fock space is not acted by the Hamiltonian. Hamiltonian has no action on all the other states. So all the other states are still of 0 energy. But these 2 states, their energy can split, and because of this hybridization. And then there is one combination of these 2 states where the energy is lower. And they are actually using this energy unit 1, it basically acquires 1 unit of energy gain, basically. So the energy is -1. The other combination with a plus sign will have energy +1, basically. And all the remaining states, I think there are 14 such remaining states will have energy 0. So that's basically the spectrum, and this is the ground state of the system. So we can see that this ground state, first of all, it's unique. There's no degeneracy. No state is degenerate with this state. And then there's a gap. The gap is of order 1. At least you have some order 1 energy gap. And this order 1 energy is set by the interaction. And then there's no fermion bilinear expectation value. If you try to evaluate anything like IKA-KB on this ground state, and it is impossible to get any expectation value because this Ki-A-Ki-B, which has 2 fermion operator, can at most only flip 2 of these bits, 2 of these zeros, right? 2, 0 to 2, 1, or 2, 1 to 2, 0. But these states, you need to hybridize between 4, 0 and 4, 1. It's impossible to connect them by any bilinear operator. So anytime you add a bilinear operator to this state, you will take it to another orthogonal state. That's why the expectation value will vanish for any fermion bilinear operator. And you can also show that the state is symmetric. It preserves the symmetry that we want to preserve. For example, fermion parity is so obvious. It's all fermion even parity state. And time reversal is maybe less obvious, but you can infer from the fact that the ground state is unique. And if time reversal was spontaneous broken, you may get twofold degeneracy. So the conclusion is that indeed, this example shows that it is possible to open an energy gap. There's a finite gap in the fermion system without generating any bilinear condensation and without breaking the symmetry we want to preserve. And then this is the example, simplest example of symmetric mass generation.
But what happens with 4 Majoranas?
Yeah.
You can split the spectrum, but
Yeah, you will still split them partially, but you still have a twofold degeneracy, which is actually transformed under the time reversal symmetry as a Kramer's doublet, and then you cannot lift that.
okay.
Yeah.
Can I ask a dumb question? If you have an odd number of Majoranas, is there just no
Then
way
it's
to...
not possible.
Oh, it's just not possible.
So you can see, it's so tricky that I just start from the beginning, say consider 8 Marana.
Yeah.
I didn't tell you what's the meaning of this 8, right? Why? Why do I need to consider 8 Marana? So I'm going to explain this. What's special about this number 8?
Make a comment about Bill's comment. So my feeling is that any odd number of Majoranas is a sick thing.
Okay.
Other people have different opinions.
Isn't it just that you don't have a graded Hilbert space?
You don't even have integer dimension.
You have a square. Your Hilbert space for one Majorana has dimension square root of 2.
Yeah.
Well, but you can have one at the edge.
Yeah. You can have one at the edge. That's
Yeah.
Yeah.
Of
On
course,
its own.
there is one on the other side too.
But then you've got 2.
Yeah, no, but formally you can think you can.
Is it because of some anomaly or something like that?
Yeah, it's said to be a gravitational anomaly.
I think that's the way to think about it, Stephen. Sure.
But I mean, what's wrong? You have anti-commutation relations. These are just gamma matrices. You can have odd number of
Squares to 0. That's it. There's just one.
No, but take 3. Sigma matrices are your Majoranas. You have 2 independent representations. There are 2 representations of those 3 Majorana fermions. There's 2 representations. That's true. There's no graded Hilbert space anymore. But that satisfies the algebra. At the algebra level, there's nothing wrong.
But there will be a problem to implement the time reversal in that case.
That may be true. I don't know. There's no maybe time reversal. I think that's right. There's no time reversal. But I don't see any problem with solving the algebra. It's a 2-dimensional Hilbert space.
The irreducible algebra does not work. Because they're real.
They're real.
Oh, okay. So that's the problem.
So I didn't want to derail the talk.
Sorry, I've just been confused about this always. So
Yeah.
All right.
Yeah. So what's special about this number 8? Basically, as you already guessed or already understand, that this should be a requirement coming from anomaly cancellation. So this 0 plus 1D fermion system with time reversal and fermion parity symmetry, or another way of saying it is called P- space-time internal symmetry, or using condensed matter jargon, it's BD1. It's a tenfold AZ class, symmetry class, BD1 class. So with these symmetry requirements, basically, these are just different ways of speaking the same symmetry. There is a non-productive global anomaly, which is ZA classified. And then let me explain this notation. This is the symmetry group, and this TP stands for topological phase, and 2 means 2 dimension. So you put the symmetry group and consider all the topological phases in 2 dimension that respect this symmetry. That actually classifies the anomaly on the boundary of these topological phases, which gives you anomaly classification in this 1-dimensional system. So your anomaly index must belong to this classification. It must be one of it, and the anomaly index actually counts the number of Majorana modes in your 0 plus 1D system. So because of this anomaly classification, you know that if the index is 8, meaning that you have 8 Majorana modes in your system, the anomaly is cancelled, and then that system is trivial. In terms of anomaly, it's trivial. So that's why with 8 Majorana mode, anomaly vanishes, and the system can be trivially gapped without breaking any symmetry, without breaking specifically this P- symmetry. So however, the time reversal symmetry is still restrictive enough to forbidden any fermion bilinear masses. You can't write down any bilinear term to achieve that. So that's why interaction is the only solution to achieve a gapping. And then we already see an example of such interaction, right? So we know this works. Any questions? Okay. So the conclusion basically is symmetric mass generation can happen in 0 plus 1D under 2 conditions. First, when there are 8 Majorana fermion modes that you cancel the anomaly. Secondly, you need to add appropriate interaction to the system. So I want to make a interesting comment that SMG interaction is not unique, but it's also not arbitrary. Okay, we just discussed this interaction, right? I use this as an example. This is also called charge 4E interaction. Meaning is very clear. It's simultaneously creating 4 electrons, let's say. And then this symmetry has a SU force symmetry actually has a larger symmetry. And there's another version of this kind of interaction that also works in the system, which is actually a spin-spin interaction. So how do I see the spins? Oh, I have these 4 fermions, right? I can group the first 2 fermions into a doublet of a SU2 symmetry. And then I can group the last 2 fermions as also a spin 1/2, basically, a doublet of SU2. And then I can say, okay, now I have one spin, another spin. I just allow them to interact with each other by Heisenberg interaction. That will basically also stabilize one unique state, which is the spin singlet state in the system. And then that's also a unique ground state, doesn't break any symmetry. And then it also has a 0 fermion bilinear expectation value. So you can see there are many different interactions, at least 2 different interactions that can produce this phenomenon with unique ground state, a gap to all excitation. Although the ground state may not be the same, but the property is the same. It doesn't break symmetry, it doesn't create any fermion bilinear condensation. However,
excuse, can I ask
yeah.
a question? So you checked that, so not only ground state is unique, you also seem to check the fermion bilinear condensate doesn't exist, but isn't
maybe they're not independent. Yeah. Maybe one implies the other.
Okay, I see.
Yeah. I just try to be cover everything.
To clear everything.
Yeah.
Okay,
Yeah.
thank you.
Sorry, is the gap the same too?
Yeah. Ground state is unique, meaning that in order to well-define ground state, there's a gap.
Yeah. Size of the gap is also
Yeah, and because it's a 0 plus 1D system, you don't have any worry about whether this gap closed, right? Quantum mechanical system, you have a gap and you have a gap. There's no CFT.
It is, so you said one is SU4 symmetric, one is...
The other is SU2 plus spin 4.
So
quotient Z4.
that's reflected in the degeneracies of the rest of the spectrum.
The rest of the spectrum.
But if you add them, can you completely have basically no extra symmetry, remove all degeneracies?
No extra symmetry.
Yeah.
That's a good question. Can you create a Hamiltonian? I think so.
If
yeah.
you just add the 2, for example.
Yeah, you just add the 2, then the symmetry will just be the subgroup, be the common subgroup of these 2, right? Yeah. You can add many.
Okay, so there is nothing special.
Nothing special about this. The reason that I want to mention is in high energy literature, when people talk about SMG, there are basically 2 very popular interactions. One is called SU4 symmetric interaction. The other is SO4, but actually it's spin 4, not SO4. But anyway, SO4 interaction. So that's basically these 2. So just to make connection to the lattice. So because this was also studied in lattice QCD, and then in their community, that's the name that was given to these interactions. So okay.
Can I ask a question?
Yeah.
One of the interactions preserves spin 7. Is that the first one? SU4 is.
No, spin 7, the original Kitaev-Fedorkovsky interaction preserving spin 7 is even higher symmetry. So this SU4 is just subgroup of spin 7. It's like spin 7, roughly speaking, a SO7. It breaks down to SO6. It further breaks down to SO4 cross SO3. Not further breakdown. I mean, break down to SO6 is one root. SO4 cross SO3 is another root.
One could ask, what's the maximal symmetry that could be preserved?
That I studied that. It's like I think you need at least more than O2. I think, yeah. You need O2 and
but the maximal symmetry. Spin 7 is the maximal symmetry.
Maximal symmetry is spin 7. Yes. I thought you were asking minimal. Maximal is spin 7. Okay, so but you can see interaction is not unique, but it's also not arbitrary. Meaning that if I'm very careless, I just write down arbitrary 4 fermion interaction. I have 8 Marana modes, right? I can use this Marana operator. This is a legitimate 4 fermion interaction. You will find that the ground state is still 4-fold degenerate. So basically, that means sometimes it won't work if you just don't design the interaction appropriately. So that's why there is this question: how do we know if an interaction works or not for symmetric mass generation? What is the gapping criterion for a proposed interaction?
Sorry, is this this sounds like
It's a dynamical question.
I mean, but it sounds also that it's just a peculiar feature of quantum mechanics. If you have in higher dimensions,
Yeah.
any interaction you add will generate all interactions which preserve such symmetries. And in principle,
Yeah.
all of them would be good enough if they're strong enough.
Yeah. More precisely, you want to ask what's the fixed point interaction. You wish to classify interaction by their RG fixed point. What are the direction? I mean, you start from free fermion fixed point. You want to flow to another fixed point where things are gapped, right? You want to know what is the most direct relevant interaction that drive along this direction, maybe. Yeah.
But I would even think that if arbitrary interaction is strong enough, is that logic not correct? That if arbitrary interaction...
This is an arbitrary interaction, and it is strong enough.
Yeah, but it's quantum mechanics. There's no RG flow.
And similar things happen in high dimension. That's why this idea was not successful, for example, in gapping 3450 model previously. People just add all the symmetry allowed interaction into the system and let it be strong, and then it doesn't work. Does it generate the interaction that gaps the system? Yes. But it also generates some other interaction that competes with the interaction you want to use to gap the system. And the result of competition direct the RG flow to some other directions. So you don't reach the fixed point you want. So that's still a subtle problem in higher dimension. So that's why this becomes a problem. And then this is one research direction, try to understand what's the designing principle of SMG interaction. So basically, we know there are two big criterions. One is on the kinematic level, you need to be anomaly free, meaning that anomaly cancellation criterion, that the fermion system must be free from any anomaly in order to admit a gap without any symmetry breaking or any topological order. And then and there's another criterion that is dynamics, that is this more subtle criterion that we don't fully understand yet, that what kind of interaction can gap the system? What kind of interaction can drive the system to this new RG fixed point with all the low energy freedom trivially gapped? However, the only good understanding of the relation between these two is maybe best understood in 1 plus 1D, where it can be proven that there is a duality between these two conditions, that they are equivalent. If you confirm that the system is anomaly free, I can give you a systematic construction of the gapping interaction. So that is achieved in 1 plus 1D, but not in higher dimension yet. But we believe that somehow these two conditions actually should be equivalent in any dimension, but there's not a proof yet.
Can I ask a question? So
Yeah.
I'm not sure if this theory is well defined as purely 1 plus 1D theory,
Yeah.
but if there is some topological order, then, and if you consider boundary, it's a question whether that boundary state is gapped or not, right? And people sometimes consider not only the gravitation anomaly, some higher central charge also gives some obstruction of gapping that boundary state. And does it captured in this class of the discussion?
Then, yeah, I'm not sure. You mean anomaly free, but has a very high central charge?
Yeah, gravitational anomaly cancels, but there is some exotic object called higher central charge, which seems to obstruct gapping the boundary state. But I'm not sure this boundary QFT is well defined as a purely 1 plus 1D theory. So I'm not sure. I'm not even sure whether this belongs to your discussion. But
Yeah, I'm not familiar with that.
I see.
Sorry. Yeah. So okay, so that's why I want to mention this example. So this example is basically a playground to show this connection between anomaly-free condition and gapping condition. So this model is a 1 plus 1D fermion model, which has a weird name called 3450 chiral fermions. It basically has 4 chiral fermions. It's Lagrangians like this. Of course, this is only the free fermion part, and there's also interaction that I'm going to specify later. So these fermions, you can see, I draw some pictures. You have 2 left moving modes and 2 right moving modes in these 1 plus 1D systems. And the 2 left moving modes, so this V, velocity, basically determines this chirality. And then the system also has 2 U1 symmetry, such that the fermions are charged under the U1 symmetry used by this pattern. So this QA is the charge of the first U1, QA prime is the charge of the second U1, such that under this U1 symmetry, every fermion operator will transform by a phase rotation with the appropriate charge, basically. So that is the charge assignment.
What is the origin of this assignment?
What?
What's the origin about this assignment?
Yeah, I explain. Why it's so weird, right? 3, 4, 5, 0. Why not 1, 1, 1, 1? But before that, I want to mention that this system can be viewed also as the boundary of 4 layers of quantum Hall insulators. So you can think of it as boundary of multi-layer quantum Hall, such that every edge mode, every this chiral fermion can be considered as an edge mode. And the existence of such an edge mode indicates that in the bulk, there's a non-trivial Hall conductance. And the Hall conductance in the bulk will be given by the charge square times the chirality, basically, for each layer, A. So, and we have 2 different Hall conductance because we have 2 different U1 symmetry. Each symmetry defines a Hall conductance in the bulk.
There can be also cross.
There also can be cross. Yes, I want to also mention that. But let's focus on the self Hall conductance first. That already gives us some hints about why 3450, why it's so weird. So this 3450 assignment is actually coming from the anomaly-free condition that you want this Hall conductance to be 0. I mean the total Hall conductance if you add the 4 layers together. So that requires that your charge assignment to be such that when you square them and then add and subtract them with each other, because the first 2 modes are left moving, second 2 modes are right moving, so that's why you have add the first 2 modes and subtract the second 2 modes. The total Hall conductance will be 0. And then 3450 is one very famous solution for this equation, right? For this integer equation of this square equals 0 and this square also equals 0. And as Lessig said, more generally, you also need to cancel the mixed anomaly, which means you don't want to mix Hall conductance between these 2. So in general, what you should think is that you should satisfy this condition where K is a matrix with a diagonal of specified by the chirality of the fermion, and then Q, I introduced 2 different Qs, Q1 and Q2, correspond to the charge assignment of the first U1 symmetry and the second U1 symmetry on the 4 fermion modes. And then the requirement for self and mixed anomaly free is basically for any alpha and beta, where alpha beta either Q1 or Q2, these inner product is going to be 0. So okay, you say that's not restrictive enough. Just by using this equation, I can find many other solutions for you. But however, we also wish that it is not so trivial, right? If you assign 1, 1, 1, 1, of course, that's also satisfying all this anomaly cancel condition. But in that case, you will have a very simple way to gap out these boundary modes or gap out this chiral fermion by bilinear level backscattering. So the reason that it's well designed as 3450 is to avoid this trivial gapping from happening. Because you can see if you have some fermion modes that is moving in this way and then carries this charge, you can't really turn on any backscattering between the left moving mode and the right moving mode, because any left moving mode has a distinct charge assignment. And then any kind of this Dirac mass term, for example, you want to annihilate the fermion here, create a fermion here, or if you want to annihilate a pair of fermion across the left-right moving mode, either Majorana mass or Dirac mass, they are all charged under this U1 plus U1 prime symmetry. So they are all forbidden by the symmetry. So that creates a very subtle situation that there is no anomaly, there's no either self or mixed anomaly, and there is, but the symmetry is still restrictive enough that it's impossible to turn on any bilinear mass term. So gapping can only be achieved by interaction effect. So that's another example of SMG.
Can this be realized in pure 1D?
Yeah. That's a research project in progress. I think the answer is yes. I think we have some construction for that, but we are not very sure yet. We still need to check. Okay, so
can I ask what is the role of second U1 prime? So what is the role of second U1 prime? Because to just restrict the Dirac mass terms, first U1 should.
Yeah. It seems like a redundant symmetry, but it's fine.
So is it useful? The construction of the.
It's kind of useful. You want to expose the full symmetry of the system. Because if you miss some symmetry, maybe because as I will explain very quickly, this symmetry dictates the interaction you can add to the system. If you miss some symmetry, you may not be correct in analyzing those interactions as well. So, okay. So now the question is, what is the correct interaction to drive SMG in this system? So the correct interaction was proposed by Yi-Zhuang and Xiaogan back in 2013. And they wrote down in their paper such a very complicated 6 fermion interaction. You can see that involves 6 fermion operators, and there are 2 of them. And then you need to apply them together. And then it is proposed that this interaction can gap out the fermion. So if you just look at this interaction, it's highly irrelevant. It's you add them perturbatively, it's not going to do anything. So when they submit their paper to PRD, it's got rejected, and the referee says that I can't imagine that this interaction will do anything to this system. So and their work was largely ignored for a long time. So that's why.
What was their reasoning? Why these were correct?
Yeah, I'm going to present the reason, but let me first show you our numerical results. So Yi-Zhuang keep pushing me, and he said, Yi-Zhuang, just get a student and simulate this system. I don't have student, you have student, you need to do that. So okay, I say okay. So I got my student Zhengmeng involved, and then we just use DMRG algorithm. We put this system on, basically we didn't realize in 1D, but we realized as an edge of a 2-dimensional multi-layer Hall insulator, and we can crank up the interaction on one of the boundary. And then in our simulation, we take G1 equals G2 equals total interaction G. If you don't want to preserve this symmetry, it's also fine. But the point is that if you turn on the interaction, and when the interaction is strong enough, indeed, it leads to some non-perturbative effect that leads to a gap phase. And what we can see in our numerical simulation is that we can measure the 2-point function of this fermion operator. And then when G is less than Gc, we see that the fermion correlation decay in a power law manner with certain scaling dimensions, delta psi. But when the interaction is strong enough, we clearly see that the correlation decays exponentially, meaning that a gap is generated.
Sorry.
Yeah.
There's some weird.
There's some weird, but you can see this weird below 10 to the 4, minus 4. DMRG calculation with a finite bound dimension, we can't really do better. So you should treat them as noise. So you can see here, it's just 10 to the minus 3. So let's say 10 to the minus 4 above is reliable data. So then yeah, okay. Yeah.
So why don't you choose a model with 3 fermions and just have charge 3, 4, 5 and.
Then you have gravitational anomaly. You have 2 left moving mode, but only 1 right moving mode, then it's still impossible.
Could I ask a question?
Yeah.
So I have lots of sympathy with this referee.
Yeah.
Coming from high energy physics, it feels wrong to me to have interactions that are strong at the lattice scale, which is what you're relying on. And my intuition is that if this 6 fermion term is important at the lattice scale, why aren't 8 fermion terms and 12 fermion terms and 124 fermion terms equally as important at the lattice? You've lost all dimensional analysis and Wilsonian RG versus relevant versus irrelevant.
Yeah.
So then I would have thought you just have this enormous phase space where you have to be tuning coefficients of many terms.
Yeah.
And it's like finding a needle in a haystack.
Well,
and yet you guys showed that's not the case. You just crank up this one coupling and miraculously you hit the phase you want.
Yeah. So I want to explain that behind this is the anion condensation theory, which actually classifies these interactions. So this is not the only two, as I said, not arbitrary, but also not unique. As you said, there are others. Where are the others? How to classify them? Are they related? So these questions can all be answered within this framework.
But also, it's a stable phase. I mean,
Yeah, within the phase, of course, you can perturb. Yeah.
It's a stable phase, but when, for example, Eichton and Preskill in the 1980s tried to do something similar for 4-dimensional theories, the argument, I think, is just as good, although they don't have an anion condensation story behind it. They just failed. They cranked up the coupling and they didn't find them.
So that means these interactions somehow need to be compatible with each other. They shouldn't fight with each other in some way. That's the key point. And then that's what I want to introduce, the gapping condition. What's the condition for interaction to live happily with each other, don't fight with each other? Yeah, that's the idea.
I have a comment and a question. So I think the point is that this gapless phase is Latinger,
Yeah.
right? And it has a parameter. And as you tune that parameter, your theory is completely under control up to that point GC, where that perturbation becomes marginal.
This picture I'm very happy
So
with.
he actually starts in some sense with this point GC rather than with the point G.
Right. Right, you should think in that way.
Sorry, but G is not the Luttinger, it's not the marginal parameter. If you were
Well-
tuning a marginal parameter until this term became relevant, then I'm delighted. That's still a story I want to
As
hear.
he's tuning G, he's also tuning.
You are going to renormalize. Yeah,
Oh,
the
I see.
Latinger
So that's
parameter.
what- so it is almost a continuum perspective
Yeah, yeah.
where you're tuning a marginal parameter.
Yeah, you turn on G. G itself looks irrelevant, it flows to 0. But at the process that it flows to 0, during that RG process, it renormalized the Latinger parameter. So the Latinger,
So what you're really doing is turning on some 4 fermion current terms.
yeah.
And
4 fermion current.
That's the Luttinger parameter.
Yeah. It gets renormalized.
Okay, then.
Yeah. It is because secretly the Latinger parameters keep being renormalized until it reaches GC, and then this interaction becomes marginal.
You find very
Yeah.
Are you going to show us the microphone model that
No,
he said that
but
it
it's
can be
I said it's just set up a multi-layer quantum Hall using the lattice model.
But you have to tell us what kind of interaction it is.
The interaction is just put this 6 fermion interaction. Whenever there is a point splitting, you just put it on neighboring site. So every site has 4 flavor of fermion, and then when you need to put 2 site 2 dagger, you put it one on different neighboring site, and then you repeat that translationally invariant throughout the system. And the simulation is done with 20 sites along that direction.
if you write down like bosonized version,
Yeah.
harmonic version for the
Yeah, it will
and
become a
the-
cosine term.
Is
Yeah.
it a simple cosine term of some
Simple in what
phase?
sense? Yeah.
Well,
I will show you the cosine term.
okay.
Yeah.
Good.
And the model is it just quantum Hall or is it Chern insulator or?
The model is just like this, 4 layers of quantum Hall, and then
So I was just asking the continuum.
discrete, Chern insulator.
Chern insulator.
You should think of its Chern insulator. It's some plaqué, square lattice, and then turn on imaginary hopping, design it in an appropriate way, and then realize 2 edges. Yeah, basically like that. It's a bit tricky. You want to make the bulk as narrow as possible, but still have 2 very stable edge state. You need to fine-tune the hopping in some way, but it's possible. Yeah, it's a square lattice model. Yeah. Okay, so what's the significance of this result? That you can turn on an interaction and gap out 1 sector. One important application is that it provides a new possibility to regularize chiral fermion on the lattice. Basically, our simulation is actually done on the lattice, at least in 1 plus 1D, and hopefully this picture can be generalized to 3 plus 1D. That's a hope. So at least in 1 plus 1D, you can write down a lattice model for this quantum Hall insulator in the bulk, and then that produced the so-called Miro sector and the chiral sector, which correspond to the 2 opposite edges of the quantum Hall insulator. But you turn on interaction on the Miro sector that leads to this gap, then you are left with this chiral sector, which nicely realizes this chiral fermion. This construction was also known as the Miro or domain wall fermion approach, which may date back to Ichton and Pascal in Priskill and in that's the year when I was born, basically. So, but the correct gapping interaction was not known back then until recently. Yeah.
But didn't you say that it can also be realized as a 1D model?
No, their discussion is a 3 plus 1D, but I'm saying...
No, that specific model with 3450 can be realized as just 1D?
Yeah, I think so, because
So
you
then
can...
why would you call it a chiral? You do not need...
Yeah, then that's an explicit lattice regularization. You don't even need to go through this Miro construction.
Okay.
But in there, my proposal is one of the U1s realized as lattice translation. You need to use this trick,
Oh, so it's
Yeah.
a
Yeah,
non-locus.
Yeah, it's not so trivial, yeah.
I see, okay.
Yeah.
It's realized as a 1D lattice, but symmetry.
Yeah, you need to translate one symmetry into lattice translation.
For what it's worth, Tin and I think we figured out a different lattice.
Yeah,
realization
maybe.
yesterday.
Yeah, we need to communicate. Okay, so oh, sure.
We think.
Yeah, okay, we can chat. So I want to explain why this SMG interaction, 6 fermion interaction, sounds very complicated, and why is that? So in fact, Wang and Wang interaction is already the most relevant interaction allowed by the so-called gapping condition. There is some mysterious condition back there to say that certain interaction, how this interaction will work. This basically means that anything simpler than this will not work. You can't really use full fermion interaction to gap out the system, even though it's anomaly free. Turns out like that. So this can be well analyzed because, as Max mentioned, that you can do a bosonization and everything is well controlled. You can map this system to a large integer liquid theory where you have these compact bosons, and this is this K matrix is described by encodes the chirality of the fermion, and then the two 6 fermion interaction that we add to the system correspond to this G term, correspond to this cosine interaction. And then it will be a L vector which specifies the cosine interactions. And the gapping condition in this system turns out to be this equation. You need to satisfy this equation. You can't arbitrarily write down this cosine. If you do that, then gapping is not ensured. But if you satisfy this equation, gapping is ensured.
Sorry, a quick question about
Yeah.
the previous slide.
Yeah.
So for that bosonization, usually, I don't know whether it's a typo or it's what you really mean. Usually bosonization, I think, is really fermion bilinear.
Yeah. Up to an incline factor, you can also relate fermion itself to a complex boson, to e to the I5, no problem with that. Okay, so the intuition basically why we need this condition. The idea is that when you add interaction to the 1 plus 1D system, you are actually condensing anions coming from the 2 plus 1 dimensional bulk. So the idea is to view this chiral fermion as a 1 plus 1 dimensional boundary of some 2 plus 1 dimensional bulk theory, which has U1 cross U1 prime gauge symmetry. And then this is like enforcing the symmetry on the boundary by gauging the symmetry in the bulk. Then in the bulk, you will have all these so-called anionic, although it's not topological order, but it's very similar. You have these excitations. And then the fully gapped boundary can be consistently achieved only by condensing the maximal set of bulk excitations, which are self-boson and mutual boson. And then in the bulk, it basically becomes a consignment theory, and the mutual statistics of these operators can be calculated in this way, basically. So by requiring this condition to be true, you make sure that operator you add to the boundary, those interactions, they are consistent with each other, they can be condensed happily with each other. So that's this condition. Of course, you also wish that this operator that you are going to condense on the boundary is neutral under the U1 cross U1 prime transformation's trivial representation, which means that it also needs to satisfy this condition. That this condition actually describes how this operator gets a phase, basically, under this U1 cross U1 prime transformation. And it turns out that the solution of these two equations is very simple. The L vector, which describes the interaction, is just given by the charge vector, which describes the charge assignment. Which means if you tell me how do you assign the U1 and U1 prime symmetry charge to the fermion, I can use this formula to tell you what the interaction I need to add to the system. And this solution turns out to unify all these criterions. If you have an anomaly-free system, which means you already have this equation equals to 0, then it automatically implies the gapping condition because of this if you follow this solution, basically. So this solution is the solution that ensures the gapping condition given the anomaly-free condition. And you also automatically ensure that the interaction is symmetric. So everything is consistent. So if we start from the charge assignment of this system, 3450, 0543, and then we apply the K matrix to these charge vectors, we can derive what kind of L vector we need to have. And we have these two columns, 34 minus 50, 05 minus 4 minus 3. These are the two basis vectors that specify the condensable operator. And then Tom just asked a question. If you have these two interactions, all the interaction can be generated. Actually, indeed, all the interaction can be generated, but all these interaction terms, they form a lattice. They form a lattice of condensable operators spanned by these basis vectors. And then this condensable operator actually forms a condensable algebra. And then the point is not to condense this particular two operator, but to condense the whole algebra. So that's I think a more higher viewpoint. And within this condensable algebra, you wish always to drive your system away from the free fermion limit by some operator that is most relevant, right? So this lattice, every point corresponds to an operator. The operator is specified by the coordinate on the lattice. For example, 3, 4, minus 5, 0 is here. And then these two red vectors are the solution we obtain by solving these consistency equations. But in fact, it specifies a lattice which has some smaller vectors, which you may not realize at the beginning. But when you look at it, these two shorter vectors are the most relevant operator at the free fermion fixed point because they are shortest. The operator scaling dimension turns out in this case at the free fermion fixed point is set by the length of this vector. So that's why they wrote down this 6 fermion interaction. It's precisely just translating back these L vectors into the fermion language, and then that gives you the interaction. But if you add this interaction to the system, indeed, all these dots, every dot corresponds to a different interaction. They will all be generated. But they are not generated arbitrarily. They form a pattern, and the pattern is a condensable algebra. So by adding these operators to your interaction Lagrangian, you can explicitly drive the condensation of the whole condensable algebra. And even though we have already been choosing the most relevant operator within this condensable algebra, but the scaling dimension of these operators is still very high. If you calculate, the scaling dimension is 5, which is much larger than the space-time dimension of this problem, which is 2. So in high-energy physics, you may be very worried by adding these, I don't know, but Juven told me that adding irrelevant operator to a field theory makes it unrenormalizable, and some may get upset with that. But in condensed matter physics, we are just very happy doing that. Adding this irrelevant operator opens up new opportunities towards adjacent phases, which means this irrelevant, right? So it flows to your phase fixed point. But if you add it strong enough, it pushes to another phase.
So I didn't fully understand that a generic operator in a generic direction would lead you somehow in a symmetry broken phase?
Yeah. Many leads to symmetry broken. Yeah. So
if I just picked a random one and cranked it up, I would still gap for the fermions, but I would have.
You will either couldn't fully gap, there's some bosonic mode left over, or you will break symmetry. Then there's still in higher dimensions still ghost town mode, but in one dimension
it's
you break
in one
symmetry.
dimension, so it would still correspond.
It still corresponds to some CFT basically.
Right. So that's what you mean.
Yeah.
So you have to hit these points which are completely gapped.
You have to hit this plane, actually. This is the 2-dimensional plane of condensable operator within the 4-dimensional cube of all possible operator in this theory. All possible vertex operator form a 4-dimensional space. There's a 2-dimensional slice. You need to hit this plane, and that's it. You are done. It's not arbitrary. Yeah.
So with this Luttinger parameter, I think Max mentioned that if you tune the Luttinger parameter, then do these operators become relevant then?
Yeah. It becomes relevant. So that's the next picture I want to show.
I see. Okay.
So if you tune this interaction,
before you get to the next slide, if you go back to your lattice.
Lattice.
Suppose that you just turned on the interactions corresponding to red arrows, not to blue arrows.
Oh, there's still a little bit problem. Then
there's a
you may miss some of these. Then it may not. Maybe it can still be gapped, but I think in higher dimension, typically this kind of thing leads to like topological order.
I think it may here as well. There's a Z5 symmetry. Which is missed somehow by these terms. So
I see.
I hadn't realized until I saw this picture that.
Yeah. It's possible. You may still have some discrete thing left over. Yeah.
What is the Z5?
The U1s don't quite act faithfully, so I think you might.
Yeah.
You might leave yourself with a Z5 topological field theory. Is that possible?
Yeah. Basically, the meaning is that this determinant, right, spanned by these two vectors is not 1. Yeah. You still have some finite unit cell. Yeah. So you are not condensing every operator in the condensable algebra. Then the operator that you miss will lead to low energy consequences. Yeah.
Sorry, just have another question. So can the charges be fractional?
charges.
Yeah, I mean the 2, 1, minus 2, 1. Can it be fractional?
Can U1 charge is integer, right? Doesn't have a fractional charge representation.
I don't know. I don't know.
Yeah, I'm not sure. Let's just be most. Yeah, let's just stick to integer charge. And yeah, this operator you need to have integer coefficient in the front. Okay, so
sorry, can I have some? So maybe it's related, but so you picked the two most relevant operators, but in theory you could have picked something extremely irrelevant as long as there's no other discrete symmetry, nothing. That would also work?
Yeah, that would also
anywhere
work.
on the lattice.
Yeah. As long as you put a determinant 1 unit cell,
okay.
that will work. Yeah.
Is there a way to see this procedure by saying like there is a UV fixed point, and if I perturb it with some tuned parameter, I get gap fermion, otherwise I go back to gapless fermion? I mean, rather than this irrelevant operator on top.
You need a range, you mean? Like a...
Yeah, I mean, I'm just saying like, maybe it doesn't make any difference. Like, is there a way to see this rather than flowing with this irrelevant operator starting from a UV fixed point at a relevant operator, depending on how I add this relevant operator, either go to
Yeah. It's more appropriate to say that I'm sitting at the fixed point and then I turn on relevant operator to go between the two faces.
Yes, I mean, maybe I didn't get exactly which one is this fixed point. This fixed point is just where you tune the radius of the pulse.
Yeah, I'm going to show you
So
what's the theory of the
I
fixed
think
point.
as you turn these on, you have a second order phase transition, right?
Yeah, it's a KT transition.
Yeah, so it's a KT transition. You can think of that as the UV fixed point. So
Yeah, that's the
that
UV fixed point.
You perturb from there and flow into that.
Yeah, that's showing here. So if you...
we would say that furnishes UV completion of the thing.
Yeah. So the UV completion is here. Is at the transition point where this interaction turns, they are marginal. Then at there, it's well behaved. You can turn it on. On one side, it's marginally relevant, marginally irrelevant. It flows to two different phases. So the horizontal axis is the coupling constant at the UV level. By our UV, we mean starting from free fermion fixed point, turn on this interaction. And then you can show that as this interaction gets larger, the scaling dimension of the interaction term itself is actually changing because the underlying Latinger parameter is secretly being renormalized. And when these dots are we've measured from our DMRG calculation. And then we can show that when this scaling dimension drops to 2, which makes this interaction, 6 fermion interaction operator marginal, that's the point where the transition happened. And when the transition happened, it's a KT transition, turns out to be. Because that's basically the KT physics. And beyond these points, basically the interaction becomes relevant and flows strong under RG that drives the condensable operator to condense. And all the remaining operator that breaks non-trivially with this condensable operator will be gapped, including those fermion operators. So that's why there's a mass generation for the fermions. All the fermions will be gapped. And you can also show that by measuring the fermion correlation function and try to extract the scaling dimension of the fermion, and you can see at the beginning almost nothing happens. When the interaction is small, the fermion just stay at the scaling dimension, which is in the free fermion limit. But when you look at this red line is the so-called experimental group. Is the edge that we apply interaction, and then we can show that the fermion scaling dimension will shoot up, and then it will reach a certain value at the critical point. While the other edge of our quantum Hall system, which we don't apply the interaction as a control group, you can see that the fermion will remain its free fermion scaling dimension forever. So this means that the interaction basically, although it's an irrelevant interaction, seems to be at the free fermion fixed point, but during the RG flow that it flows to 0, it actually secretly renormalizes the Latinger parameter to a point such that at a certain critical value, it basically makes the interaction term marginal. And then that's the UV, that's basically the critical theory. And at that point, the transition, the SMG transition happened. And at this transition point, the fermion typically has a larger scaling dimension compared to the free fermion limit, because passing this point, the fermion will be exponential decaying. So it will decay very fast. So you imagine if you have a fermion correlation that is decaying faster, you should have an increasing scaling dimension before you reach that gap phase. So that's, I want to say, it's like a precursor of fermion fractionalization, which will be the topic maybe after the break. So I think it's the time to break. Yeah.
Can I ask a question?
Sure.
So after knowing this knowledge, so can't we add the for Fermi current interaction to directly control Latinger parameter and after that?
Control the Latinger parameter. Maybe, yes, possible.
And after that,
after that, you add
V6
yeah.
fermion interaction may generate.
Yes, yes, that's also possible. Yeah.
And actually, you pointed out some tension between the worlds of condensed matter and high energy physicists. But shouldn't this, is there really a tension?
No, I don't think there's
no
really
tension, right? It's
right?
just, okay, right. It's
Yeah.
just that the high energy theorists should not have used the free fermion scaling dimension.
Yeah,
That's all, right?
Yeah,
They were just wrong in this.
Yeah.
Okay.
Yeah.
Right.
Next.
So, do you understand the critical point? How many relevant perturbations there are? How many marginal perturbations?
Yeah, there are two marginal, the two interaction terms, both of them are they are independent marginal perturbations.
There is also Latinger parameter.
The Latinger parameter is the only tuning parameter in the system. That's the relevant, if you want to say. That's the tuning parameter at least.
Why? I thought it's equal to theory, so I thought there is more than.
Yeah, what is the harmonic?
Yeah, Latinger parameter you tune, and then there are two cosine terms.
But
it's equal to theory, right? So it's
yeah.
not just one Latinger parameter.
Yeah, your harmonic.
Yeah. There are two Latinger parameters.
Oh, it's a matrix.
It's a matrix, yes. So
that's what I'm asking.
Yeah, there are two Latinger parameters. It didn't. In our paper, we have the full structure of the V matrix, which exposes the structure of all the Latinger parameters. But here, if you impose a symmetry requiring G1 equals G2, it turns out you can eliminate that to one.
Is that some discrete symmetry that you impose?
Yeah, if you impose that, you can restrict to one Latinger parameter tuning. Yeah.
And then it's just really a KT transition.
Yeah.
Okay. How long the break do you want to make?
5 minutes or?
It's 5 minutes?
Yeah.
Okay, 5 minutes. 5 minutes and have a coffee, you come back.
So that's what analysis is. But there's no tension in the 1 plus 1 equal, right? This is what you're imagining, that you somehow stay in the same phase while continuously adjusting the.
Set. So it's some kind of charge conjugation symmetry? What is this symmetry that you are?
This parameter, this operator isn't relevant there, it is relevant here, and is that correct?
Maybe.
As long as you say yeah, I would say
commutation is also like
all your fields have different one charges, so how can you permute them?
Actually, maybe I can ask you, so I tried to book Airport Express. I have very early flight on Sunday morning, and we already booked. I didn't realize I need to book so early.
Well,
Are there some
I'm just
other
thinking about
cab
the symmetry,
services, taxi services which service the airport that you would recommend?
I think the best one is the Airport Express or the
365, but it's
yeah.
already booked. They replied
it's already booked.
that they already booked for Sunday morning.
all your fields have different.
There is also like a taxi service from the airport, which is there. I can grab the number for you. But I never used the services. They must have like.
That sounds very interesting.
Recently.
maybe.
Are there some other ways to get to the airport, like bus or something?
There's bus.
But it was.
There are two Latinger.
Is there lift or?
Yeah, here there's no lift, but there's Uber.
Uber.
Yeah.
I don't have Uber.
That's how I had to go, and they work really early in the day. I used Uber before.
But if I My flight is 6 a.m., so I need to be at the airport.
Yeah, I'm just asking. I'm asking
For
whether you can
4,
avoid
right?
the last
Yeah.
Yeah.
to have a direct.
I think you can get there by Uber because I have
And then
taken
the other thing is
flights
about
from
this,
Newcastle like
gapping condition.
like
right?
7
So
in the
actually
morning,
the
and I
bulk,
got an Uber
it's
like
this, to have this
5,
algebra, to have this
4.5.
Lagrange subgroup,
So
whatever.
you can
Doesn't
also do
actually
that.
have to be zero.
But I can check some other airports that can schedule and
Yeah, I
so
would,
So the
I
gapping
would rather
condition on
have
the edge
something
is kind of
scheduled
strong.
because it's
definitely.
don't want to miss my flight
It's
and then
wonderful.
miss another flight.
It's kind of one way go, one implies the other.
I
but
didn't
the-
realize
this
usually
way is-
like it's almost not good to book too early. I'm just used like it's better like best to book a day ahead or something, but it seems like I missed.
Very nice, very nice.
Tried to booking and we replied that we already booked.
Yeah.
seeing the same things.
This is the right order of the decomposition and the data
Did they resubmit the paper after the numerical results? Or?
They are going to do that like in a few months.
Okay, welcome. We're good to go?
Yeah.
Okay, we're rolling. We're continuing.
Thank you. Thank you all for coming back. And then, so in the following part, I'm going to present a symmetric mass generation example in 2 plus 1D because, of course, we want to generalize to higher dimension that may be more interesting and useful. So how can we extend our knowledge, our understanding about SMG that I just talked about in 0 plus 1D and 1 plus 1D to higher dimension? Well, in low dimension, it's very special. 0 plus 1D is quantum mechanics. You can solve it exactly. 1 plus 1D, you have this Luttinger liquid theory. It's well controlled. 2 plus 1D and higher, all this technique doesn't quite apply. So it requires new ideas. And the idea I want to advocate is called fermion fractionalization. It provides a uniform framework to understand SMG critical points in higher dimensions. And the hypothesis is that the physical fermion that in your original system fractionalizes into deconfined bosonic and fermionic partons at and only at the SMG critical point. So something fractionalized to deconfined partons at the critical point only, this is the theme that people in condensed matter physics, we call it deconfined quantum critical point. It's a quantum critical point where the deconfinement of some particles only happen at that point. But it's a fermionic version in the sense that it fractionalizes the fermion, yes.
Sorry, is there a reason to believe that it's always a critical point? It's not
no, there's no reason, but there is a lot of numerical support for that.
For particular examples.
For particular examples. So of course, it doesn't need to be. Yeah.
But about the phase, you do not. Once you are in the phase, you do not need to worry about it.
Yeah. In the phase, it's basically like a confining, and yeah. In either side of the phase transition, I'm talking about the SMG transition when the fermions start to open a gap. At that point, it's DQCP.
But once you are in this phase, aren't you interested in the phase where the fermions?
I'm more interested about the transition than the phase, because if I understand the transition, I also can understand the phase on the two sides.
But with the transition, you may have an issue whether it's critical or not.
Yeah. I'm more interested.
Phase is a simpler
Yes.
question.
I'm more interested in understanding the case where the transition is continuous, which was supported by a lot of numerical experiment. Yeah, I'm interested in that. Okay. So in the phase, of course, it's easier to understand. You don't need this gauge series. Yeah. Okay.
I see. So you can say there is a gap phase where the fermion without mass generation is fully symmetric.
Yeah.
So that's a simpler question.
Yeah. Okay. Basically, there are 2 questions: whether there exists an interaction to tune into a gap phase, whether that phase exists, right? Okay. That's question number 1. Question number 2 is, if such a phase exists, you tune the interaction, do you go through a continuous direct transition? Okay. And then magically, many numerics support a continuous direct transition, just as the case we found in DQCP. Okay. It doesn't need to be a continuous direct transition, maybe, but it happened to be that. So there must be some reason behind that. So that's why we want to understand this.
And for the first question, you do not need fractionalization.
You do not need. For the first question, it's almost following the scheme that I talked in the first part. That's okay. You want to understand anomaly cancellation. You want to design appropriate interactions, things like that. Yeah. So let me tell you the model. The model is a 2-dimensional, 2 plus 1D lattice. Which is related in condensed matter. In condensed matter system, it's called bilayer graphene, a very hot topic nowadays. And then it's basically electron hopping on a honeycomb lattice. But this honeycomb lattice basically is carbon, made of carbon, forming this graphene material. And the graphene has 2 sheets lying on top of each other. And then that's it, basically. So the fermions are basically the electrons in the material. And then on every side, you have 2 layers, the first layer and the second layer. And then on each side, each layer, meaning that on this carbon atom, the electron carries 2 spins, up spin and down spin. So the electronic operator, you have the site index, layer index, and the spin index. That's the hopping term. So every electron of different layer, different site, they just hop independently on this honeycomb lattice. So that's very simple. That's the hopping term. And then you also have an interlayer interaction where the spin of the electron interact with each other by a spin-spin interaction due to, it can arise from Coulomb interaction, but I don't want to explain those details. But there's some, you imagine that there's some spin-spin interaction where the spin operator is written in terms of this fermion in this way by considering if you drop this sigma index, if I do that, that means I'm thinking the CIL as a doublet and the spin SU2 symmetry, and then you can define the spin operator. So the model only has one tuning parameter, which is J over T. And then we did some numerical simulation back in 2014 to show that this model has a direct and continuous transition from a Dirac fermion phase to a fully gapped symmetric phase through a critical point when you tune this interaction versus kinetic energy ratio. So in the weak coupling limits, or say weak interaction limits, if you drop this interaction, this hopping term, you can solve it by diagonalizing the band structure. And then you will find that it's 2 layers of graphene, and we know famously graphene has these Dirac fermions at the Fermi surface. Basically, each layer produces 2 Dirac fermions at the corner of the Brion zone of the graphene at so-called K and K prime points. And if you have 2 layers, of course, then the band structure will be degenerated. But yeah, but that's essentially the picture at the at weak coupling. So at weak coupling, the ground state will have fermion field all the way up to this Dirac point, and then you have gapless fermion in the system. However, if you turn on the interaction and make it very strong, then if J is so strong, you can even ignore the T term. But if you just look at this J term, the Hamiltonian just decouple to each side. Every side, you just interact the spin across the layer, interact independently on each side that stabilize a singlet state across the layer. This interaction is nothing but the interaction I just mentioned in this 0 plus 1D problem, right? You can turn on spin-spin interaction also to stabilize the SMG ground state. And this and in that strong large J limit, the ground state of the system is just a product state of spin singlet across the bond, across the layer, throughout the system. And then this state is also, you can show it's a unique ground state. It has a gap to all excitations, and it also preserves all the symmetries. I haven't mentioned what's the symmetry. Well, this system has a little bit more involved symmetries. It at least has U1 plus SU2 plus Z2S. Let me explain. So the 2 U1 symmetry correspond to the U1 charge conservation of these electrons in each layer independently. You can see that there is no interlayer hopping. And then each layer, electrons just hop in the graphene layer independently. They don't turn over to the next layer. Of course, this is an ideal model. In reality, it does happen, but let's ignore that. And then you have 2 independent U1 charge conservation. But there's only one SU2 spin symmetry because the spin interact between the 2 layers. So they lock the SU2 together, so there's only one total SU2 spin. And then there's also a very interesting, this Z2S, which is the sublattice charge conjugation symmetry. What it does is that it takes the fermion operator to its complex conjugation, to its C dagger, basically, but it's also an anti-unitary transformation that takes imaginary units to minus. And the detail is not important, I just explain things. And there's also lattice symmetry, of course. In the honeycomb lattice, you have translation, rotation, reflection. The point is that although it looks very complicated, it turns out if you check it carefully, all these symmetries of the model rule out any possible fermion bilinear mass term. You can't write down any bilinear term to get out the system at the present, if you want to respect all these symmetries. The most important symmetry, it turns out to be this conjugate symmetry and translation symmetry. These 2 symmetries are sufficient to protect this system from being gapping out by bilinear gap.
Is
so
this Z2 symmetry time reversal?
It's kind of like the time reversal. Yeah. But there's some subtlety. Not worry about that. So I want to show you there's an attempt to create a bilinear gap. For example, by breaking this 2 U1 symmetry, you can introduce interlayer hopping to the system, And then I should say this is only an attempt to do that. And then if you introduce such a hopping, interlayer hopping term with a particular staggered pattern, let's look at here, when this hopping coefficient is opposite for A and B sublattice, then you can diagonalize the band structure again, and you will find that there will be a gap open for this Dirac fermion, just trust me. So this is a way to create a bilinear term, a gap for these Dirac fermions. However, as we already mentioned, it must break some of the symmetry. And in this case, it breaks the U1 minus symmetry, the so-called interlayer U1 symmetry. U1 minus is basically a combination of these two U1 symmetry with an opposite rotation. So if you rotate the first layer fermion with a positive phase and second layer with a conjugate phase, then the mass term, because it's like interlayer hopping, will rotate by twice of the phase. So you can see this mass term will break the symmetry. And then you also break the very crucial sublattice symmetry as well. But that basically means you can't really just add this term explicitly to your system. It will going to break the symmetry explicitly, but you still wish to find some way to explain this gap phase, right? Because cramping up interaction, we reach a gap phase. We want to understand how that happens. So that doesn't happen by spontaneously breaking the symmetry and generate this mass term. So it must happen through something. But something actually is related to this interlayer hopping. So that's what we learned from condensed matter physics, that if you cannot open a gap for a physical fermion system, you can try it on so-called fermionic partons, on gauged fermions. So those physical fermions are restricted by symmetry. You are not allowed to add bilinear term. But those gauge fermions, if you gauge it, maybe you can do that. There are examples like quantum spin liquids. One way to understand that in condensed matter language is it basically failed to open a superconducting gap in a Mott insulator. And that leads to a superconducting gap actually for fermionic spin-ons. Well, if you fractionalize the spin into spin-ons, into spin 1/2 fermions, for example. And I want to make an analogy that symmetric mass generation is very similar. It basically opens up a fermion bilinear gap in the, it's basically a failure to open up a bilinear gap in the system because of the symmetry requirement, but you can do that for fermionic partons via fermion fractionalization. So if you don't understand this condensed matter jargon, don't worry. I'm going to show you the explicit construction. But I just want to say this construction is very much motivated by a very important topic in condensed matter called quantum spin liquids. And then the idea is basically consider writing down the electron operator C as a product of a boson operator B and a fermion operator F, where the C operator on each side and each layer has two components, which is upspin and downspin. So you can think it as a doublet, and you can rewrite the doublet as a fermion operator F times a boson operator. Boson you should just think as a scalar field. You just multiply the scalar field to this fermionic spinor field. So you are basically splitting your electron into so-called bosonic parton and fermionic parton just by rewriting that. But this rewriting is called fermion fractionalization because you fractionalize the original physical fermion. It comes with a price, or maybe a gift. The gift is basically the emergent gauge structure. Because if you look at this expression, this B operator, you can go through a gauge transformation, meaning that you can perform a U1 rotation on every side and in every layer independently to this B operator by this rotating this phase angle. You can do the same opposite phase rotation for the F operator, but if they combine together in this way, then the C operator, which is the physical fermion, the electron operator, is not going to change in any way. So this kind of internal phase rotation between the B and F operator is a gauge redundancy that you introduce to the system because you want to use such a redundant description to describe your original fermion system. And then this redundancy turns out to be a gauge structure. It becomes an emergent gauge structure. And the emergent gauge group will be, again, U1 cross U1, because you can do this kind of rotation independently on the upper layer and on the lower layer. So you have two different emergent U1 gauge group. I want to put the tilde in. Yeah.
So if you get back to patterns, then because of these emergent gauge fields, don't we end up with
Then you-
topological order?
Yeah, you still end up with some gauge fluctuation at low energy. But then it relies on the fact that these gauge groups are compact and U1, and it's in 2 plus 1D. There's Polyakov mechanism, monopole proliferation, it confines automatically. So you get rid of those.
Because there is no Maxwell.
It's not a Maxwell theory.
I see.
The punchline is that. Yeah. Okay, so the emergent gauge group is U1 tilde cross U1 tilde. I put the tilde to distinguish that from the U1 plus U1 symmetry. So here is a table of the charge assignment of all the fields that I introduced. So the physical fermion, of course, it will be gauge neutral. It will be neutral under the U1. All these U1 symmetries, gauge structures. It will only carry, for example, the first layer electron will carry one unit of charge under the first U1, and then representation 2, which means spin 1/2 under SU2. And then maybe the second layer does another thing, and this interlayer hopping is SU2 symmetric in terms of spin, but in terms of the layer, in terms of this charge, it basically removes one fermion from the lower layer to the upper layer, so it has this kind of charge assignment. So what we are doing here is basically splitting this C into B and F, such that B carries both the U1 symmetry and also the U1 gauge charge, both the symmetry charge and the gauge charge. But now F only carries the gauge charge, such that if you combine B and F together, for example, if you look at this B1 and F1, if you combine them together, the gauge charge cancels, such that it goes back to this fermion. But the symmetry charge, it's like you are attaching the symmetry charge to this fermion, such that this fermion becomes the physical fermion. So that's the construction. But using that construction, you can see, previously we are not allowed to turn on this interlayer hopping mass term, because this mass term breaks the symmetry. But now we are going to be able to turn on this mass term for the fermionic partons, because the fermionic parton doesn't really carry any of this U1 plus U1 symmetry, only carries the gauge charge. So this mass term turns out only breaks the gauge symmetry, break the gauge group. Basically, it breaks these two U1 into the diagonal U1 that is combined rotation, but it doesn't affect the symmetry. So that's how you can create, in a sense, this is an Anderson-Higgs mechanism. It's like you create some gauge fermion and then go through an Anderson-Higgs mechanism such that you only break the gauge structure, not breaking the symmetry you want to preserve. So that's a way to give fermion a mass without breaking the symmetry. So that sounds trivial, right? So at this point, it's not so non-trivial. So now we can have, with this understanding, we can write down the field theory description. And the field theory is also not very difficult. It's basically a QED theory in 2 plus 1D, but it has 2 layers. Basically, because the graphene has 2 layers, you write it down for each layer separately. In each layer, you have a scalar boson, which has only one component. And then you have a spinor fermion, basically Dirac fermion. But the fermion has 4 components because we have basically 2 valleys. Remember that in the graphene band structure, if you diagonalize the band structure, you have 2 Dirac fermion at 2 different points of the Brillouin zone. That's so-called 2 valleys. In high energy physics, that's just the fermion doubling. And then you also have 2 spin. That's the internal degrees of freedom. So you have 4 flavors of these fermions. And then you also, the boson and fermion are coupled together by the dynamical gauge field, AL. And this little a is the dynamical U1 gauge field. It's a one-form gauge field, and then it's dynamical, it fluctuates. And it's independent. You have 2 sets of this gauge field for each layer. The 2 layers are basically, they don't talk to each other. They're independent. And then you have also, I also introduced 2 background U1 gauge field to track the symmetry, because the most important symmetry I wish to keep track of is the 2 U1 symmetry that's conserve the electronic charge separately in both layers. So now you can use this theory to understand the SMG transition. SMG happens by tuning a parameter which corresponds to the bosonic scalar field mass term. This second, yeah.
In this division method, C to F times B, like you have a larger gauge symmetry to make arbitrary scaling.
Yeah, you can maybe promote it to SU2. That's safe.
Just no, it's non-compact because you we scale F and B with opposite that layer, or?
I don't know. I just fixed the B and F charge from the beginning.
So this is a different theory.
Are you sure because of the fermions is that they have a lattice points, right? So there's a commutator fixing the size. I think it's only a phase rotation. Because the commutator is like F dagger, F is 1, right?
Yeah,
one side. So
it's the canonical structure. So
Yeah.
yeah.
It's just a phase.
Yeah. Okay, so then let's try to understand what happens if I tune this parameter R. So if this R is less than 0, that basically means that the scalar boson wish to condense. And if the bosonic parton condenses, there's a Higgs mechanism that's because you can see the bosonic parton coupled to the background gauge field and the dynamical gauge field in each layer independently. So it basically, once it condenses, it pins the dynamical gauge field to the background gauge field, they're equivalent. And then the dynamical gauge field here will no longer be fluctuating. It will be pinned to the background. And then basically this fermionic parton regains the U1 plus U1 symmetry and becomes a physical fermion. So the effective theory that describes this system becomes as if you can rewrite the F fermion into just rename the variable, and then into a C fermion, which corresponds to the electrons, which carries both the first layer and second layer charge conservation U1 symmetry. Right? So that goes back. That means if I is less than 0, this gauge theory basically reproduces the free fermion physics, the Dirac semi-metal physics. So you are in the Dirac semi-metal phase. So that's corresponds to the weak interaction phase. However, when I is greater than 0, then the bosonic parton acquires a gap, and when it is gap out from the low energy, and then it decouples, then this dynamical gauge field basically decouples from the background symmetry, and it just becomes a gauge field that can fluctuate independently in the two layers. But then we need to rely on an assumption. The assumption is that under this gauge interaction, due to energetic reasons, the fermionic parton wish to spontaneously develop a parton Higgs mass. The so-called parton Higgs mass is basically a F1 bar F2 mass for this Dirac fermion, which basically corresponds to that interlayer hopping term that I introduced on the lattice previously. So if you have that mass term dynamically generated under the gauge interaction, then it has two consequences. The first consequence is that it fully gap out all the fermions from the low energy. Secondly, it also hits the gauge field AL. Remember, there are two independent gauge fields for the first layer and second layer. But now, if you have an interlayer hopping of a gauge charged particle, then basically you're locking the gauge fluctuation between the two layers. So the gauge group is broken down from U1 plus U1 to the diagonal U1. And then but the diagonal U1 gauge fluctuations are only remaining low energy fluctuation. But then this fluctuation, because U1 is compact, and then it automatically confined by monopole proliferation through the Polyakov mechanism. So up to this point, there's no degrees of freedom left at low energy. The boson is gapped by this R greater than 0. The fermion is gapped by the Higgs mass. The gauge group is gapped by confinement. So you are left with nothing at low energy. So you realize a trivial phase without topological order, without symmetry breaking, and then this is the SMG insulating phase. Yes? Oh, then maybe you can, yeah, okay. Then you can add 4 fermion interaction explicitly to drive this. Maybe. So that means you still need to. Okay, so maybe I was wrong, not by gauge interaction, but by adding additional 4 fermion term in order to drive this instability. This assumption, this.
Is there anything wrong within the effective theory to add those terms?
Nothing is wrong, but it just means that you have more fine tuning. It's not so beautiful. Yeah.
Is there each sector NF for QED with
I think it's NF equals 2 QED. Sorry, NF, you're right. NF equals 4 QED, and then a monopole. Yeah, you mean how does the monopole trap fermion and things, quantum number like that? I think it just follow the conventional unequal analysis. You have I think you have 4 Majorana modes trapped in the monopole, right? And then you fill one complex fermion mode and they transform under SU4. I may be wrong in this detail, but something like that. I think it transforms as a SU4 fundamental.
Is there a monopole involved by symmetry?
Oh, is that a
Monopole charge 1 allowed? Or is it higher?
I think if you have this U1 combined monopole, right, you can trap fundamental and anti-fundamental and they neutralize, which makes it allowed by the symmetry.
So you mean the phase term should not appear because of that?
Yeah, first of all, there's no non-trivial Berry phase, I think. There's no Chern-Simons term generated by this mass. Yeah, we analyzed that in our paper. We checked those monopoles are symmetric, yes. So I may not be able to reproduce immediately right here, but we did carefully check all these monopoles, at least the monopole I want to condense is symmetric.
It's clear this doesn't have an anomaly,
right? Because on the lattice model level, you can explicitly show, you can gap it, right? And you can also, of course, show that it's anomaly free. Yeah.
But that's essentially because of two-layer structure, is it?
Yeah,
one layer has
a problem. Two layers
don't.
Yeah.
This is related to the Z8 anomaly for time reversal.
That's right. In 2 plus 1D. You can see I have 8 fermions. Each layer has 4. Yeah. I secretly built all this in the model, but I just didn't emphasize. Yeah.
Your gauge field is also on lattice immediately dimension.
Yeah. Yeah. My gauge theory is also within the lattice, so.
No, but it also has like explicit lattice realization.
Yeah. Okay, so now we know that the transition must happen at I equals 0, or some renormalized fixed point around I equals 0. So this is a deconfined quantum critical point because away from this I equals 0, either are greater or smaller than 0, the gauge field are Higgs or confined, and all the partons are deconfined and at and only at this critical point. So this is a fermionic version of DQCP, where the fermion gets fractionalized instead of the bosonic order parameter, like NEO and VPS was fractionalized. So it's very similar to DQCP, but just a fermionic version. But then, with this gauge theory, what we can do is we can take this theory and in each layer, the 2 layers, basically they are decoupled. Each layer is a QED3 theory with 1 flavor of scalar field and 4 flavor of spinor field. And then there has been works on how to do a large N analysis by pushing this NB and NF to large limits, and then try to estimate the scaling dimension of the physical fermion C as a composite particle of B and F. And then the calculation there shows that the scaling dimension of this fermion is around 1.3 if you extrapolate to this limit, and then it is greater than 1. 1 is the scaling dimension of the free fermion in 2 plus 1D. So the electron 2-point correlation should decay faster according to this prediction, that it should decay 1.3 times faster in terms of the power, and then at the SMG critical point with a larger power compared to the free Dirac fermion theory, and that is a prediction of this gauge theory, and it has not been numerically tested yet, so maybe, yeah, that's my next project. Maybe I will try to do that, but I will try to say that it does create some predictions. This theory is not just a story. It actually has some prediction power. And then I also want to tell you a story that deep in the SMG phase, you can also make sense of this gauge confinement. That if you are in the SMG phase very deeply, then your fermionic parton has a very strong parton Higgs mass, which basically means that the fermion parton is hopping between the 2 layers. But if you have some fermions hopping between 2 sides, then you have two fermions, you want to occupy the two sides, and they hop to each other, then basically this hopping leads to a bonding state and anti-bonding state. The bonding state will be occupied by a pair of spin singlet fermions. So basically that's the description of this spin singlet fermion occupying the bonding state. But then if you expand this wave function on every side, you can show that it basically split into two parts. One part still depends on the phase structure of this mass term, and the other part it doesn't depend on the phase of the pattern Higgs mass. But what's the significance? Because in order to impose the gauge confinement, you basically want to disorder or gauge Higgsing. It's like you want to disorder this U1, this mass term, because this mass term itself is not gauge neutral. So one way to understand this mass term is gauged, meaning that you can open up the mass term, but this mass is just fluctuating in terms of the phase. So if you have the mass term that fluctuate with in terms of the phase, then in the resulting ground state wave function, any term that is proportional to the phase of the mass term will get annihilated by the interference, by the destructive interference. And through this calculation, in the end, we will see that it predicts that on every side after the gauge projection, the wave function on every side is nothing but a spin singlet across the layer. So that reproduce the ground state exactly at the large J limit. So that's just an argument to say that this gauge fluctuation picture maybe makes sense because it actually also reproduces what we know in the strong interaction limits. But using this picture, actually, we can do more. Because with this understanding, in some sense, the SMG mass is basically the parton bilinear mass. Or you can say it's like the physical bilinear mass, but disordered by certain fluctuations. So then that means we can try to infer what's the Green's function in the system. Fermion two-point function, we can make some prediction about that. For example, if we start from a free fermion theory with an explicit bilinear mass like that, we know how to calculate the two-point function. The answer is like this in the momentum energy space. But then we use this idea, but then if you look at this free fermion, let's go back to free fermion, the trivial bilinear mass, then it basically produces a few features. For example, this Green's function has a pole along this dispersion relation. But looking at this dispersion relation, you can say, oh, then the fermion excitation is a well-defined quasi-particle. It has an energy gap, which is proportional to the mass absolute value, and that is the rest mass, which is the energy gap at the minimum of the dispersion. And then there's also a notion of inertial mass, which basically related to this curvature of the dispersion relation near k equals 0. And that turns out also to be this mass term, m. And there's also something called bilinear mass condensation, because if you are in this system and you try to measure the fermion side-by-side expectation value because you have an explicit mass term, then you expect this expectation value to be at least related to this mass term, maybe by some other function that is depending on mass, but at least it's not non-zero. You expect this is to be non-zero. So that's our intuition in the free fermion limits, that when you open a mass to this relativistic fermion, you simultaneously acquire a rest mass and inertial mass, also bilinear mass condensation. However, all these consequences, they may not be related in general, right? So SMG is indeed a scenario where it still produces a rest mass and an inertial mass, but it doesn't produce the bilinear mass condensation. That's why I want to explain, because you can think about the SMG as disordering the fermion bilinear mass term without turning it off its amplitude. So you still keep the amplitude of the mass term like m squared. This is still fine, because m squared will survive the random fluctuation, because the fluctuation is like those gauge fluctuations is just changing the phase angle of this m mass, and then the absolute value square is perfectly fine under averaging, but m itself will average to 0. So if you just go through this argument, then you can try to argue that maybe in the SMG phase, at least deep in the SMG phase, when this mass parameter is not fluctuating very strongly in terms of amplitude, then you can have an expression for the fermion correlation. But this Green's function is very different. This Green's function has two dispersion relation along the poles, And then across the pole, the determinant of the Green's function will change sign because across the pole, there's a sign change in the numerator, basically. But here it's very different. If you look at this Green's function, it still has a pole due to the denominator, but there's also a zero structure because of the numerator. Because if you look at here at k equals 0, when k equals 0, right, the denominator doesn't vanish, but the numerator, because it's linear in k, vanishes. It's precisely because you don't have this mass anymore. So if you try to plot the Green's function as a function of frequency and momentum, and then you try to plot its value of determinant of the Green's function, you will see that they will have very different structures. And then the SMG fermion will have a Green's function which still produces a pole with a gap, with an energy gap. So you still have a rest mass, and you still have some curvature here, which means it has inertial mass. But you just don't have fermion bilinear condensates because of this zero structure. The reason is that if you calculate the fermion bilinear expectation value, that corresponding to this integration, but because the Green's function now in the SMG phase is kind of an odd function in K, so this is actually required by symmetry. It's not an accident. So basically integration goes to 0. So basically it's a symmetry requirement that you don't have fermion mass condensation, but you can still produce well-defined quasi-particle excitations above the excitation gap. And the excitation gap, which is the rest mass, is also equal to the inertial mass in this case because of this Green's function respect the Lorentz symmetry as well. So that's our understanding of the fermion Green's function in the SMG phase. And it turns out that the existence of zero in the Green's function is a very robust non-perturbative feature of SMG. It can be used as a basic smoking gun evidence for SMG. And then I think I'm running out of time, so I will skip the proof. There's a non-perturbative proof using the techniques of topological integers, and then you can show that it's a robust feature. And maybe I go to the summary and I open to questions. So in summary, SMG is a novel mechanism to give fermion a mass without generating bilinear condensation, allowing us to getting out fermion without breaking symmetries. And it has two conditions on the kinematic side. You need to cancel the anomaly dynamically. You wish your interaction can really drive you to that trivial gap, RG fixed point, but this is less well understood. And then it has some interesting features. At the transition point, it is proposed that at least for higher dimensional SMG, it's a fermionic D2CP with non-trivial, which is a non-trivial CFT with enlarged fermion scaling dimension. Enlarged in the sense that larger than the free fermion limit. And then inside the SMG phase, the fermion Green's function has very peculiar structure of zeros across the momentum energy space. And that is like a very strong feature of SMG. And that is also a feature that can be checked very easily using numerics, because you can calculate fermion two-point function, and immediately you get information about Green's functions. And it has many applications, such as lattice regularization of standard model or grand unified theories. It leads to new candidates of non-SUSY dualities. It may lead to new perspective on strong CP problem classification and so these are high energy applications. There are also condensed matter. On condensed matter side, we are very interested in classifying or constructing interacting fermion SPT states, and many of these construction relies on symmetric mass generation, and it may also lead to new insights of maybe pseudo-gap physics in high temperature superconductor, because there it's also a problem of how to open a gap on the Fermi surface without breaking any symmetry. So maybe things are all related. So yeah, that's what I want to share today. Thank you.
So I was wondering, in your bilayer model, is it really a good analogy to the D2CP in a quantum antiferromagnet, because you need this the bilayer structure, right?
Yeah.
The spin system, if you do a bilayer, we just get a Wilson-Fisher in all three critical point, and we can easily get the trivial, singlet product states. So wouldn't it be better if you have something in a single layer, and that would be the true analogy?
Yeah. So the bilayer is basically two copies of
right.
of the spin DQCP. Yeah. So the point is that, yeah, of course, I agree, it's better. If you want to study Neo VBS DQCP, then single layer, just do that. But here we want to study a different problem, which is this SMG. And SMG is very different from the...
Right, but still it's a very special situation when you have the bilayer, right?
Yeah.
So then how can you draw all these big picture consequences and applications if it relies on such a special feature?
I mean, this is not the only model that exhibits 2D SMG.
I was specifically asking about that model, because you argue that it's the DQCP analogy.
Well, this has good content of things to allow this type of transition, but his transition is from semi-metal, basically, gapless
to gap phase.
Because I'm just saying that if you can accomplish something in one layer which seems much more difficult, maybe that's the more appropriate.
No, it's impossible to realize SMG in one layer because you only have 4 fermions and the anomaly is D8 and then it doesn't saturate anomaly and you're done.
But shouldn't it be possible to have some DQCP with fermions in one layer?
If you ask that general question, maybe yes. But
he wants a trivial gap phase.
But if you want a trivial gap phase, then one layer is not possible.
I mean, could you do spin 1 or something like that? That should have. That doesn't have an anomaly.
Maybe, yeah. That's true.
I mean, I guess that was my sort of criticism. I mean, not really criticism, my question. I mean, we can easily have quantum phase transitions into trivial gap phases in spin models as well, but those are less interesting in some sense because the trivial gap phase, right?
Yeah. But for fermion system, it's more interesting. If you have a spin system and trivial.
It's more, but still, I think it would be even more if you could have some other kind of gap phase.
Okay, sure, yeah.
I couldn't understand the consequence of the last part of your discussion because so you discussed the 1-point function of the psi condensate, but so isn't it the direct consequence of the fact that so psi should break some kind of should be carried under some symmetry, and also you are establishing the symmetric trivially gapped phase by symmetric mass generation. So can we get an immediate? Can we immediately conclude from these facts that in psi should vanish?
Yeah, yes, your logic is right.
Yeah.
We can immediately conclude by symmetry argument that this is 0. But the point in this slide is that this important feature is reproduced by this Green's function. This is a non-trivial proposal. I propose that deep in the SMG phase, the fermion 2-point function is described by this formula. This formula may sound very familiar to you, like it looks really similar to the free fermion gap Green's function, but there's a crucial difference that on the numerator there's no this mass term, and that makes a big difference. And then I'm trying to justify that this Green's function, it does satisfy all the symmetry requirement. It also produces the gap for the fermion. So this is the Green's function to understand this SMG phase.
But since psi is charged under some symmetry, so isn't it somewhat dangerous that just looking at 1-point function? So, because, for example, if we compactify space, symmetry cannot be broken. So, if we just naively look at the 1-point function, we always get 0. So, shouldn't we look at 2-point function?
You say maybe there's a disconnected piece in the 2-point function.
Yeah.
Of meaning 4-point function fermion.
4-point function of fermions. That decays exponentially.
That goes to a constant, and you're in symmetry broken.
Yes, that's true. That's just the condensed matter shorthand notation of symmetry, of saying, It's you should always think of this expression as a statement of correlation function decay exponentially.
Any more questions?
Yeah.
Could you do this fermion fractionalization in 4D?
Yes. Yeah, true. New theory. Yeah. It's basically like you have all these Yukawa terms, and then you just need to take away those symmetry you want to gauge. There's some symmetry H, right, you wish to gauge. You assign those to some bosonic pattern, and the remaining, all the fermion content doesn't need to change. All the fermion content just go from the physical fermion to the fermionic pattern. You still put the fermionic pattern in whatever original dispersion. You just introduce a scalar field to insulate the fermion from those symmetries you want to gauge. Then you can safely gauge things. Those recoupling construction.
Thanks.
Could you apply that in 2D model that you try to fractionate there and have?
Although that's not necessary, but this picture still holds. Like
Right.
the 3450. There's
Of course,
also
it's not that. I mean, well, I mean.
There's also a gauge understanding there.
I see. Okay.
Yeah. So things are unified. It's not different dimension. It seems that after this talk you get the impression that every dimension has a different story. No, there's a unified story. So that's why we write this review paper wishing to unify the pictures.
There are no more questions. Let's break for lunch and reconvene at 2:30.